Okay, I think we're ready to get started. Thanks for joining us on our Thursday webinar series. This is a topic regarding reliability. We've recently added capability to do a reliability analysis of your power system networks within EasyPower. It's a module, works standalone, so there's no interdependencies on any other modules, and you can purchase it on its own or add it to an existing EasyPower configuration if you have one. And let's jump into it. So I will. You can go ahead and ask questions if you have procedural questions regarding the webinar or so on. We will. You can ask those, and Nicole will be answering them. If you have technical questions, I'll take a look at those at the end of the webinar and answer them for the audience. So you can just go to the GoToMeeting tool and type in your questions there. Throughout the webinar, though, I do like to ask questions of the audience so that I know that you're engaged and not sleeping or doing other work. So I might ask you some flash questions. Go ahead and type them in, and we can see what the consensus is. With that, let's get started. My name's Stan Spencer. I'm here at EasyPower. I'm a mechanical engineer, but I have a background in statistics, so that's why I'm presenting this today, and I was involved in the development of this module. So the ultimate thing that we're interested in with performing a power systems analysis for reliability is to determine what ultimately it should come down to cost for you. So we'll be quantifying, to do that, we have to quantify what's the uptime, the downtime of all the components and the branches, the load branches in the system, and then put cost numbers on those. And there are a couple different, just at a high level, types of cost. There is, of course, your repair or replacement cost of an individual piece of equipment when it goes down. And then there's also the time of the cost associated with time for a particular load branch to be down. So if you've got load branch that's, operating a piece of CNC equipment that is producing parts that, based on the part rate production, if that load goes down, it might be $10,000 an hour or something like that. So we'll be able to enter all of these costs and quantify them at the individual branch level and system level, and then use that information to be able to compare between different scenarios. The module is based on IEEE 493, which is commonly referred to as the Gold Book. It's a spec that has been around for a long time. I think last modified 10 or 12 years ago. There haven't been any recent changes. And then the other thing that we'll be referencing relative to this spec is what's called Annex Q, which is data that's been compiled over decades on historical empirical data failure rates for different types of equipment, 2-winding transformers, 3-winding transformers, cables, etc. We have all of that data in EasyPower, and you can leverage it. We'll be able to model multiple scenarios with the EasyPower Scenario Manager and allow you to create, like let's say I want to look at my weakest piece of equipment and look at increasing the reliability of that, maybe purchasing a different piece of equipment. What does that do to my overall reliability of the system and ultimately my cost, and does it justify purchasing that equipment? Maybe I want to add redundant equipment, typically power, whether that's in the form of an additional utility branch input or backup power generation, diesel generators, batteries, transformers, etc. One of the things that we do with the Annex Q data is we automatically map it to the equipment in your one line. So, we've tested this module on some sample files that have 6, 8, 10,000 buses. It would take you an awfully long time if you had to go through each one of those and reference Annex Q and add that data in. Even if it were already in the product, doing that manually, equipment by equipment, would take a tremendous amount of time and probably not even be worth it. So what we do is we automatically attempt to map that reliability data. As I mentioned, the Annex Q data is classified by equipment type, and so with a click of a button, map it all to your data, populate the data, and then allow you to perform the analysis. Our algorithm analyzes up to 3 levels of redundancy, so primary plus 2, and that's unique in the industry. And that third level of redundancy, there are diminishing returns in terms of improving the overall system reliability, but we felt that it was important to do, partly to solve, at least to some extent, some of the sample problems in the 493 spec. The biggest challenge with doing that, though, is you've got to go through, like I said, when you've got a one line that has 10,000 buses in it, there are an awful lot of paths. And so our developers have done a great job in terms of developing the algorithms to go through and find those paths and the redundant paths. And we do that. I mean, I solved one recently, 7,000 bus system in a matter of minutes. So we've come a long way in terms of that system solve time. So let's go through some simple examples. I'll go through a few examples here that are really simple so that you understand the concepts, and then we'll get into showing you the product, and then go with questions. So let's imagine you've got a utility coming in that fails. Now the numbers that I'm showing you here are completely made up and are meant to, I've made them up in a way that it makes the math easy, so that we're not struggling with that aspect of it. So let's say you've got a utility coming in, it fails 10 times a year, and each time that it fails, it takes 5 hours to repair. So you can say right off the bat that you can plan on 50 hours a year for that utility being down. So the question is, what's the probability that utility A is unavailable at any given time? That's going to be 50 hours divided by 8760, which is the number of hours in a year. Now, with leap years, it would actually be, a little bit more than that, but the spec, 493 spec, standardizes on 8760. So the probability would be 0.00571 that utility A would be down at any given time throughout the year. Typically, these numbers are measured in our annual failure rates. So then we've got a bus that's coming in, switchgear panel, whatever you want to call it, but it's failing 20 times a year, but again, it takes 5 hours each time to repair. So that bus will be down 100 hours a year, and now we've got double the failure rate of the utility, 0.01142. Now we've got a load, and you can add a failure rate on the load itself if you want to, if you know the failure rate of, let's say, the piece of equipment. If you want to factor that in, you can. I'm not doing it in this webinar. So we know now that the load total is unavailable for 150 hours a year. 150 divided by 8760 is 0.01712. All right, so now let's look at the cost aspect. We've got the failure rate of the load, which is what we're interested in ultimately. The repair cost of the utility is $5,000 every time it goes down. So I've got 10 failures a year, $50,000 a year in total that it's going to cost me to repair that utility each time it goes down on an annualized basis. Bus A, repair cost is 1/10 of that, $500. So that's going to be $10,000 a year for 20 failures per year. So my total downtime cost per year, so this is a second type of cost, and we'll go into where this is defined and how it's defined in EasyPower. But downtime cost per year. So this gets back to that load is a piece of CNC equipment that's making parts. And when that machine goes down, I'm losing, as the owner of that facility, I'm losing $9,000 an hour in lost revenue because I'm not able to make those parts and then therefore sell them. So 150 hours of downtime per year, which is what we had previously calculated here, times $9,000 an hour amounts to $1.35 million a year. So add that then into the repair costs of $60,000 and we get $1.41 million a year. So another thing that we do in EasyPower is we provide a Pareto chart of the downtime. So a Pareto chart, for those of you who aren't familiar, is just a stack ranking of all of the contributors to, in this case, unavailability. So it's going to be from largest to smallest, and typically there would be 10 or 20 items here, and then there would be diminishing returns, a long tail there that we're not really interested in because there would be a small effect of going after them in terms of improving them. In this particular case, what we've modeled here is the unavailability on the left y-axis, and on the right y-axis, it's the cumulative percent. So in this case, it's pretty simple. There's only two components, the bus and the utility. The bus is the larger factor. It factors in 100 hours of the 150, so that's 2/3. And then this is the cumulative chart referencing on the right y-axis. So this will become more useful and relevant the more items that you have, but that's the principle. So then the question is, what are my options for improvement? I can look at increasing the reliability of my individual pieces of equipment. Maybe I've got some old equipment or something that needs to be repaired or replaced. So I would look at that first. Typically that's going to be your low-hanging fruit. And so in this particular case, I would focus on bus A first. My returns are going to be greater there. So examine what, am I going to get any reliability improvement by repairing or replacing that equipment? The next thing, and we'll go into an example of that. The next thing I could do is I could actually reduce the repair time and or the cost of repair. I'm not going to provide an example into that. It's self-explanatory, but it's another thing we could do. And then the third thing I'll go into a little more extensively is adding a redundant branch or redundant power source, so that when the first branch goes down, I've still got power to that load. So let's look at installing a more reliable bus. So our utility stays the same failure rate, same cost, repair cost annually. But now instead of failing 20 times a year, the bus fails 10 times a year. So now it's only down 50 hours a year instead of the 100 as before. So it's essentially got the same failure rate as the utility, but the repair cost is lower. It's 1/10 of the cost because the cost was less to begin with, $500 a shot. So now looking at the load, summing up down to the load, I'm unavailable for 100 hours a year instead of the 150. There's my probability of being down at any given time throughout the year. And my downtime cost now is 900 grand a year because I'm only down 100 hours a year instead of 150. My total annual cost due to all failures is 955. And obviously these are all made up numbers here in terms of failure rates and costs and so on. Individual results will vary. You need to look at your own data, obviously. Let's look at adding a redundant power source. The first branch stays the same, 150 hours a year. There's my probability. Now I add a second branch. Let's make the assumptions that this utility is a separate source so that it's not tied to any of the reliability of the components or the substation or anything related to the first utility. In other words, so that when this utility goes down, this one, the reliability of this is orthogonal to it and it will still be up. The bus we're going to assume is the same type of bus and therefore it's going to have the same failure rate. So we're down the same amount on this branch. Now I haven't gotten into the complexity of, these are in a true backup mode and so therefore they're powered off and that might influence the probability of failure. I'm not getting into that complexity today, but that might be an influencer in your actual system. So in other words, let's imagine that this is a diesel power generator. Well, if the generator is off most of the year, then it's not wearing out, it's not going to increase the probability of failure, and so its numbers might change. But that's not an assumption I'm making here, just to make the math simple. Okay, summing up down here, so the probability that the load is unavailable is this probability, 0.01712, times this probability. So now I'm at 0.00029, and 8,760 hours times that. Now I'm down 2.57 hours per year versus where I was at before, which was 150 hours a year. So vast improvement, but as with all things in this life, we have to factor in cost. So we'll do that in a few slides to see if that reliability improvement is warranted by the cost of the additional branch. So just looking at that system, the repair cost, is 60 grand on each branch, and then the downtime cost 2.57 hours times 9 grand an hour. For the productivity loss is 23 grand a year. Total annual cost due to failure is 143,130. It's about a tenth of what it was. So dramatic improvement, and dramatic improvement over what we did before, which is just having or cutting the failure rate of bus A in half. Okay, so now here's our Pareto of downtime. We've got 4 components in the system now, so this cumulative chart starts to make a little more sense. But these are individual failure rates. Again, the buses are the least reliable, and those were ones that we would want to go after. You might at this point say, well, let's, I've added the redundancy, but I still need a little more to eke out. If you were choosing components to go after in terms of increasing or decreasing the failure rate of those individual components, you'd start here before moving here. All right, let's just, for argument's sake, say we want to add an additional redundant power source, okay? So now we're really taking advantage of that third order algorithm that I mentioned at the beginning, being able to analyze this problem. So as before, the probability of failure for each branch is the same, but the repair cost is also the same. So 60 grand times 3 branches. Now I multiply them across the board. So 0.01712 cubed is this number, 5 zeros and then a 5. Multiply that by 8760. So now we're down 0.04 hours per year. So when this one fails, this one kicks in. When this one fails, this one kicks in. The downtime cost now, due to my lost productivity of that load being down, is 360 bucks a year. Pretty minimal. But remember, I've added an additional 2 branches, so I have to factor in the repair cost of those 2 branches. So 180 grand a year versus 143 grand a year for this scenario. So a little worse. So let's compare the different scenarios across the board. And ultimately, we've gone through these numbers. Let's go through it in one. Or one column. So the system we initially started out with had a failure rate of 150 hours a year. This is our probability of failure. And if you hear the term, now what's my reliability? Take 1 minus that. So it'll be 0.99 something. You'll often hear in the industry people talk about, well, I need 4 nines or 5 nines or 6 nines. They're talking about that 1 minus number. And so you can do that. I haven't done that here, but you can use that as a number to compare if that's useful to you. Here's the repair cost was 60 grand. The downtime cost 1.35 million. So the total annual cost of the failures is $1.41 million. Okay, now I've made, just again, keep the numbers simple. The cost of my utility connection is 500 grand and the cost of my bus is 50 grand. So my system cost is 550. I need to add this in to my annual cost of failure. So we're almost $2 million here. Now let's look at the improving the bus reliability. The only difference here, aside from the reduction in unavailability, is that I've increased the cost of the bus. I've made an assumption that it's going to cost me $25,000 for that improved reliability for that bus. But the system is down less. So this total system net cost is 1.5 million versus this almost 2 million. Now we're going to add a redundant branch to the original series system. And our total annual cost of failures is much less, 143,000 versus 1.4 million. But I've had to add an extra utility connection, so another 500 grand, and then an additional bus, so 100 grand. So the total net cost is 1.2 million for that. And then in the redundant branch case, my downtime cost is negligible. My cost of repair is more than this one. But wow, the cost of additional equipment really is starting to hit me. So now I'm at 1.8 million on this one. So the point I wanted to make here is that there's a diminishing return for redundancy. And if you were looking at the net cost across the board and all your options, this is the one that you would likely choose. So in EasyPower Scenario Manager, you'll be able to model these different scenarios, run the reliability analysis. It's going to spit out these costs as well as the failure rates and the downtimes, and you can put this information together pretty easily. Let's jump into the demo of the software. As I said, this is a beta version of the product, and we've made a few changes since the version that I'm showing you, so things won't be quite like this, but they'll be very close. First thing is that we are shipping with the product in the samples directory. There's a reliability folder. We're shipping the first 8 sample problems that come with the IEEE spec. This problem, if you're unfamiliar with it, has 2 utility sources, utility B and C. It's got 4 backup diesel generators, 2 of which are required to power the entire system at any given time. There is obviously all connected together with a complex array of buses and equipment. And then our loads are down here. So this is our lighting bus. There's some mechanical buses here powering some induction motors and so on. There's a non-critical bus. So let's go through how we would analyze this. So the reliability is accessed all through one button on the ribbon. And the first thing we're typically going to want to do is populate the equipment with the reliability data. So let's assume that you've built your one line, you've got it all done, and either you own the facility and you want to see what your expected downtime and downtime costs are, or you're a consultant doing work for someone who owns a facility, and you want to add that extra step of service into them. This is done pretty easily once you've got the one line already constructed. So click the reliability button, import library to current one line. So there's some options here. Right now we've just got Annex Q, but you'll have the ability to make a copy of Annex Q. So this Annex Q library here is non-editable. We want that data to be uncontaminated and never be allowed to change unless the 493 committee changes it, in which case we would provide an updated file. But what you would be able to do is make a copy through the dialog boxes, super simple. Make a copy of that Annex Q library and then edit the values, or you can create your own clean library and add your own values, either one. So now I also have the choice of overriding existing reliability metrics within the file. So if I've manually entered things into the file, I may not want to overwrite those. But in this case, let's say that I do. So I'm going to hit import. So it says I've updated 34 pieces of equipment. Let's take a look at the database view. So there are 2 ways. Let me go back. There are 2 ways to enter data. As always, you can double click on a piece of equipment and you'll see a new tab here. In addition to the power flow, harmonics, etc. tabs, I'll see a reliability tab. I can enter the failure rate. 1.956 in this case is the typical utility fails about 2 times a year. This says per 1,000 feet. That's a bug in this version. That's only going to apply to cables, so that'll be gone. And then what's my repair time? 1.32 hours per event. Now there's some additional boxes here. What's my replace time? That's not relevant because I've chosen, it says action upon failure. Do I want to repair or replace this piece of equipment? I've selected repair, so the system's never going to look at the value in this box, even if I enter one. Same goes for cost, so I could enter the cost here. What's my repair cost? I think before we said $5,000 for the utility, and 500 for that bus in my simple system. But if I've entered repair, then if I enter a replacement cost, again, the system's not going to look at it. So I can at this point also, I can individually enter import and select my library. Now, because I'm in a piece of equipment here, which happens to be the utility, it's going to look at the category as defined by NXQ and say, oh, that's a utility. Here are your options, okay? And then all types listed. So again, there are no options here. Let me pick something a little more interesting, perhaps. So select this transformer, come over to the reliability tab, and hit import. So NXQ is my only choice. I've got 3 types of transformers in the category, and then within those, let's say I pick transformer dry, then here are the options. So when we attempt to map this data to your system, we will automatically look at the settings of the transformer to look at, is it air cooled, is it oil cooled, what are the KVA ratings, etc., and do our mapping. At this point, you can override them though. And let's say I do that, I hit import. Now you'll notice this value is actually changed. Now, if a value didn't come in here for the repair time, it's because there wasn't one in the library. You can enter one here or in your library or both. Okay, that's one way that you can populate your data. The other way is we've added this database view, or it's, could be called a spreadsheet view. So you've got your equipment types here, the names, and you'll see that for a number of these, there is no data. And because we already did the auto mapping into here, it means that the system didn't populate any data. We weren't confident in the information we had to be able to automatically map it. So you could enter it. I could come in here and I could say my failure rate is 0.005 and my time is 5 hours, and I could enter a cost. And then do I want to repair or replace on failure? So if I come down to something that's been mapped by NXQ and I say I change that to 2, then it's going to say entered manually, because we don't want you thinking that, this was actually NXQ data. You need to be able to distinguish that. I could revert that though and go back to what was there. So this is all of the reliability data and cables, breakers, everything in the system for us to be able to perform an analysis now. All right, going back to the one-line view, another thing that we'll want to define are system cost impacts. So again, this is a table that comes from the 493 spec, where they've said, based on the business type, whether it's a commercial, industrial, or an organization, institution, there are known costs, typical costs for being down. So if a business is down, has a 2-second outage, there's no cost associated with that. If it's 1 minute, then it's $379. 20 minutes is $744, and so on. And we interpolate between these values. So when we actually calculate it for every for the system, if it comes in at 5 minutes, then we're going to interpolate between those. And additionally, we will extrapolate beyond the 8 hours based on this curve. There's also a spot here where you can enter your own data. So if I say, whatever it might be, maybe this is a nuclear power plant, right? And then I know my downtime costs as a function of these interruption times, then I can enter that there. All right, so I think we have enough information to perform the analysis. So at this point, we'll hit reliability evaluation. We're prompted with a question. So do we want to do a first, second, or third order analysis? So if I were back to this problem, then it doesn't make sense to run a second or third order analysis because there's no redundancy in the system. I can run it and the results will be the same. The reason we give you this option is because if you know you don't have the redundancy, or you don't want to take the extra time that it takes to perform the analysis, which again, even in very large bus systems is only a few minutes. We've given you that option to be able to choose. So in our case, we even have greater than third order redundancy, but I'm going to pick that and then hit start. So that's it. Analysis is done. I've calculated my failure rates for all of my individual components and branches and the percent contribution of each so that I can plot a Pareto chart and choose which components to go after, which are contributing most to my unreliability. Most importantly, now I'm down to my load branches. So this is what I care most about. One they focus on in the spec a lot is the lighting bus. My failure rate for that is 0.021. The average repair 5 hours, and the cumulative unavailability is 0.1 hours per year for that lighting bus. And we've got costs over here. Some of you probably call us on the fact that these aren't quite right, and you'd be correct. And again, that's because I'm using an earlier preview of the software here. And the reason we haven't released it to the general public yet is because it's not done. But they will be correct and everything will be right by the time it's made available to you. We have provided an additional row here for you, which is not something that the 493 spec discusses, which is a system summary. So, I mentioned at the beginning, I'm a mechanical engineer. I've spent years designing products, physical products. And in that world, when you talk about reliability, you ultimately need to know what it is for the system, not just individual load branches in this case. So we've summed everything up there. And at the system level, we're saying your cumulative failure rate is going to be 0.15. And your unavailability per year is 0.57, 0.58, which is 4 nines on the reliability aspect. Sorry, availability. So that's it there. Now let's do a Pareto chart. Just click the button. In particular, I'm plotting unavailability. One of the questions I have for you to ponder is, why are my main buses contributing most to the unavailability? If I look at my spreadsheet view, if I look at the failure rates, the ones with the highest numbers are my utilities. So they're almost 2 times a year, but my buses, main bus A, for example, it's 0.00949. So the question is, why are they showing up here as being most influential on my reliability? And the question has to do with redundancy. So if I come back to the one-line view, if I can find it, what it's saying is that once this utility goes down, it's 2 times a year, and then this utility kicks in. And then when that utility fails, then my generator buses kick in. But the problem is that these are the weak links in the system. So even if the utility is providing power, if that bus goes down, I'm not providing power to that lighting bus. So it's also on a lower order. When we talked about that first, second, third order redundancy, it's on a lower order. And I can talk about the method we use to perform the analysis. The spec calls out 5 different methods. We use what's called the Cutset method. And I can go into that if we want at the end, if there's time, and explain that more in detail. So let's open it up for questions. And then if there's time and people want, I can go into Cutset or we can just end. So, all right. The question is, seems the key buses are not redundant, but utility is. Yes or no? That's absolutely correct. So that's basically what I was just explaining. And let me go into Cutset a little bit more to explain that. Let's imagine that we've got a system with a power source, and then we've got a load at the end of the system. And these individual boxes here are different components, pieces of electrical equipment in the circuits. Ignore what they are for the moment, and let's assume that they all have the same probability of failure, which is 0.01. In order to get current to the load, I can go through this path, which is AC. I can go through BD. I can go AED, or I can go BEC. Okay. Now the way the Cutset method works is you're going to then construct a matrix that identifies each of the components in the system. So in our case, we've got A, B, C, D, E, and then here are the 4 paths that we defined. Step 2, if any of our columns contain all ones, then this is a first order cut. So if, for example, we didn't have this B component here and everything had to go through A, then A would be a first order cut set. In other words, if A goes down, system goes down. But it's not. So now we're going to create a combination of the 2 columns. So multiply, or A and B, not multiply, sorry, but A and B would be 1, and for path 1, A and B for path 2 would be a 1, A and B for path 3 would be a 1, and A and B for path 4 would be a 1. So now looking at that, so that means that's a second order cut set. So any which have all the ones are second order cuts, A, B, and C, D in this case, which means that if A and B go down, then the system goes down. If C and D goes down, the system goes down. So those are second order cut sets. And then repeat the process for third, and then in this case, ADE and BCE. So ADE and BCE. So that's a third order cut set. If that cut set or that cut set, all 3 of those components goes down, then the system goes down. So now let's look at it from a reliability perspective. The probability of failure of the first cut set, which is second order, A and B, is 0.01. We said the reliability of each component was 0.01, so 0.01 times 0.01 is 0.0001. Same on this cut set. Now this cut set is a third order, so it's going to be 0.01 cubed. Same here. Now we're going to sum these reliabilities, and our probability of all branches failing is 0.0002. I know I went through that really quickly, but that's the cut set method in a nutshell, and that gets to ultimately why those buses are the weak links in the system as opposed to the utilities. Annex Q database, consider the age of the equipment. So it does in a way intrinsically, in the sense that the equipment was monitored for decades, and they brought in thousands of data points or hundreds of data points or tens of data points depending on the equipment, and all of that equipment had different ages. So the question, the true answer to the question is, I think what you're getting at is no, because I think what you're looking for is, can I go and say, if, for depending on if this is new equipment, here's my failure rate. If this is equipment that's had 1,000 hours on it, here's my failure rate, and so on. You can't do that with the data. It's all averaged in. And the other point about that I'd like to make is the assumption that we make in 493 is that the failure rate is based on an exponential distribution. So what that means is that the failure rate is constant. So whether the equipment is brand new, I just installed it on the floor, or it's 1,000 years old, my failure rate's the same. Is that real? It is not, but it works in most cases, because like if you have if you're familiar with a bathtub curve, which is that the failure rate of most systems, physical things in the real world, have a bathtub shape to them, which is that you have infant mortality failure rates and at the very start, and then it tapers off. You weed out those infant mortalities, and it tapers off at a low failure rate. And then as equipment ages, it starts to spike up again. Now imagine just plotting a straight line through the middle of that bathtub, maybe where the level of the water is. That's your average. That's what is represented in Annex Q, and is what's represented with an exponential distribution. So hopefully that answers your question. When will the module be released? It'll be released in early May. How much is the new reliability module? Depends on, as with all things in our software, depends on the number of buses. I don't remember the pricing exactly. I think for the unlimited bus version, it's, I want to say $5 or $6 grand. And then down to the 50 bus version is probably, $2 grand or something. From a practicality point of view, is reliability assessment module by EasyPower practiced heavily in the industry? Good question. I don't know the answer to that exactly. We built this module based on requests from customers. So there is a need out there, and I suspect that the need will grow as a way for facility owners to look at reducing their costs due to downtime. So from a consultant perspective, I think it's a natural fit because, if you've got the one line built, as you saw, within a few clicks of the button, you can have your results, and maybe the customer will want you to do a little optimization between equipment costs and downtime to give them the best solution. But you can provide an additional service and definitely pay for the cost of the module in the first analysis that you perform. One thing I didn't go over is providing the results. So all the results are, that kind of Excel spreadsheet view of the results. You can just right click, send to Excel, cut and paste in Word. Everything is super simple that way. The Pareto charts are easily just copied into PowerPoint or Word or whatever you want. Does it provide polished summary reports? I wouldn't consider what I just described polished. It's probably something we'll be improving over time. Some of our other reports are a little more canned and polished from that perspective. But really, there isn't a lot of additional information that you need to do to polish them, or a little additional work to polish them, taking that information into Word. For high-level clients that are not, so provide polished summary reports for high-level clients that are not tech savvy. So I think I answered that question. Does Annex Q include additional categories beyond what were shown in the table? So data center. We can show you what's in Annex Q. When you get the product, you can see the categories yourself. There's nothing specific to data centers in there. There are a number of annexes, so Annex A through Q, that cover other things. I think N covers high voltage transmission lines, things like that. We've included Annex Q. It satisfies our base of customers, which is commercial and industrial customers. We can add those additional annexes as required. Some of them are just outdated and were compiled into Annex Q, and some are independent, represent independent equipment. I'm not aware of data centers being represented in any of them. But if you have the data, you can add it easily to your own library and then map it in the future. Okay, it looks like that's the end of the questions, certainly the end of my presentation. Thanks for attending. Hopefully this was useful to you, and the video will be available soon. And then if you have any questions, please reach out to me. Thank you.